Alright, we're going to look at heat transfer and we're going to look at states of matter. Now, this stuff is actually quite easy, but you need to use the right vocabulary when describing it, so be very, very attentive to the key phrases that I'm going to use. Let's start off. Solid, fixed shape. The atoms are arranged in a regular structure, and it's incompressible, so it can't get more dense. Let's wait until it comes back round. We'll look at a liquid next. A liquid is still very, very dense. It takes up the shape of the bottom of the container. Look as it goes. There you go. And more importantly, the molecules can flow past each other. And it's the fact they can flow past each other, still really close together, that gives a liquid its properties. So solid, regular, liquid takes the shape of the bottom of the container. Gas. Now gas, they're much further apart, roughly 10 times further apart. They take up the entire shape of the container. They move fast and they move randomly. Okay, get those key things. We're not going to talk about plasma, we just need to know about those three. We're going to draw them, and the best way to draw them is to show that it's a fixed shape with a solid. Notice that they're just as far apart, they're the same density, very, very similar for a liquid, and for a gas we draw them far apart. I could even draw arrows on them to show they're moving randomly and really fast. Think about our phase transition. So I've drawn them. I could go from a solid to a liquid, we call that melting. Liquid to a gas, evaporation or boiling. Now, evaporation just happens at the surface. It can happen at any temperature. But boiling is all the way through. Think of your kettle. Every bit of it's bubbling. And that only happens above the boiling temperature, or the boiling point. Alright, gas to liquid. Well, of course, that's condensation. Think of the condensation on your window. Liquid to a solid, we call that solidifying. Freezing is kind of just water, but freezing is okay. Solid to a gas, well, that one's sublimating, you will have heard that from chemistry, and just for those ones that want to know everything, we've got deposition. Alright, so if I'm using these key words, we're going to say solids vibrate. We're only going to use that word vibrate for solids because it means about a fixed position. And a closed pack, we're going to say it's a regular structure. As you put in more what? Well, I put in more energy and heat, I shake them up, they vibrate more and more. When you put in enough energy for liquids, the atoms move about out of their positions and they move quicker. And this means that they're still densely packed, but they can flow past each other. And for a gas, we've got evaporation, or we've got boiling, and that happens at temperatures. So evaporation happens at the surface, happens at any temperature, and boiling happens throughout the liquid above the boiling point. That's quite a nice set of notes if you want to write something down. Let's look at this one. Common misconception: if I had a metal thing and a wooden thing and I held on to them, which one feels colder? Well, which one feels colder is the metal. Which one's at the higher temperature? You might think they would, but no, they're the same temperature. They just feel differently. And this is all because of conduction. A thermal conductor is something that will allow thermal energy in the form of vibrations to pass through it easily from one side to the other. When I heat it, can you see? It's vibrating faster and it's transferring, just the neighbour, the energy from neighbour to neighbour. Okay? You can think about these two things as well. Now that's a normal conductor. In a metal, I'm even better because I've got delocalized electrons. And those delocalized electrons, instead of going 1 to 2 to 3 to 4 by passing on by collisions, I can go from here, because it's delocalized, I can go woo, bang, over there. I can transfer it really quickly throughout. Yeah? So a metal is a better conductor because of those delocalized electrons. Now, the next way of transferring heat is convection. And you might have seen a demonstration like this convection tube, where you see some coloured dye moving around in this convection current. Now, we need to explain it in terms of these things. Okay? First of all, the particles are moving by Brownian motion or random motion. We heat them, and that means they move faster, it means they get further apart. If they're further apart, that means their density is less. If the density is less, then a lower density will rise to the top, because the heavier stuff is going to fall down, and it's going to push it upwards. And that makes it go up to the top. Well, when it goes to the top, it's going to encounter some of the cold stuff that's there. and it's going to collide, because remember these are particles that are moving, very densely packed, they're already colliding, and when they collide, they're going to lose their energy. Then they're going to lose their energy, close together, more dense, sink, and the whole cycle repeats itself. Now, because the particles need to move, convection currents can only happen in fluids, and fluids are liquids or gases. It can't happen in a solid. Let's look at this one. Why would this lady be wearing black? And why would you wear white in the desert? Well, this is all about radiation, the third type of heat transfer. We need to know that matte black is the best absorber and emitter of energy. Well, why would I want to wear it? Well, actually, because it's going to emit your energy. So if you're in the shade, it will get rid of the heat you produce, your body produces really well. Why would I wear white? Well, of course, that's going to reflect. It's a bad absorber. So it's going to reflect all the light from the sun back away from me. So some people wear black because it's a good emitter, and some people wear white because it's a good reflector. Okay? Think about applying those ideas when you're talking about radiation, which is the transfer of energy from waves. Convection, I need that fluid there, I need to be able to flow. Conduction, well, where does that happen? Because I need to be vibrating, it always happens between a solid and something else. It could be a solid to a solid to a gas, a solid to a liquid, but there's always got to be a solid there. Okay? Those three types of heat transfers, we come across them all the time. But there's one more. There's evaporation. It's why you feel cold when you get out of the swimming pool. It's why when you blow across your hand, it feels cold. Why? Because you're evaporating sweat or water from your body. Why does this reduce my energy? Well, if you've got all of these particles, they're not moving at the same speed. Some are moving faster, some slower. And when they evaporate, the highest energy evaporates. They become a gas. Well, if you lose all the high numbers of energy, you're going to reduce your average. And the average kinetic energy is what we call temperature. So temperature is average kinetic energy. So the highest energy you lose, this reduces the average kinetic energy. Therefore, the temperature, because it's a measure of that average kinetic energy, goes down, and that's why evaporation loses heat. This is one to look at. I'm going to plug up the answers very quickly. How does this get heated? Think about it. Use those types of transfer: conduction, convection, radiation, and evaporation. They're not all important here. Use at least some of them. Well, the oven heats the air inside of it. The air particles hit the pie, and that's going to transfer energy to it by conduction. The solid pie crust is going to transmit energy through it by conduction. And then the liquid in the centre, the nice hot apple stuff, is going to convect, is going to transfer energy by convection. When it's going to cool down, it's going to lose energy by radiation, it's going to give up waves. It's also going to heat the air and cause convection currents. It might also conduct to the plate, so think about these three things. There might be evaporation there to lose some energy. That's unfortunately why apple pie gets cold. Alright, look back, do the test, see if you've got it all. Good luck.